So for the remaining classes, most of them are going to be on my iPad. So quite different from the previous stuff. And we're going to actually do some more technical things like math-related stuff and whatnot. I'm going to start with pointing out some important notices. So there's no tutorial today. You should have got an email about this. We haven't really covered anything to go over, and there's probably not enough stuff after today to go over. So there's no tutorial, so don't go to the tutorial at 4 o'clock today. Second thing is I have office hours today right after class, basically, so you can just like follow me there if you want. If you have any questions about the course, about what I taught today, about life, I don't know. Yeah, there's a question. Okay, let's see if I can do that. Is this any louder? Okay, is this okay? Okay, it doesn't like actually show up here as what volume level it is for some reason. Cool. Yeah, so office hours, if you have any questions about anything, come to that. I'm impressed to see how many people came in person today. That's reassuring. And then the last thing is the course notes. So there's going to be some things I cover today that aren't there yet. Once again, this is me slightly changing up things and including extra details to things that I think are going to be useful. And yeah, so I apologize for that, but I'll be adding that to the course notes shortly so you guys can follow there and so on. Okay, so now we begin with the technical content. So the stuff we're going to be interested in is reviewing math. And in particular today, we're going to be reviewing like these, I guess, 3 topics, which is going to be called sets, vectors, and functions. Okay, and maybe many of you think this is already really simple and know all this. Maybe not. We're going to try to get everyone to the same level of knowledge because, yeah, there's this, I was kind of battling with how much I wanted to go over the math stuff because in some sense it kind of maybe misses the point of like all the machine learning stuff and makes it kind of confusing why you need to do all this math. But then from another side, if you don't know the math, I think it's going to be quite challenging to understand like properly what's actually going on and why we do a lot of things in the course. And from like the last year when I TA'd this course, I really noticed that a lot of the students struggled with a lot of minor like notation and details and this kind of math stuff, and it really took away from their ability to like understand things. So I really emphasize like putting the time in now to understand this stuff, like the math details, because after that, I think everything will follow very, very clearly, hopefully. Okay, so before diving into the math, I'm going to try to motivate what this is actually going to look like. So yeah, I'm going to kind of give you an example of how we're going to use the math to write our problem, like the supervised learning problem setting. And after that, we'll dive into the math. And there's a question. Are you going to be posting these? Yes, these will be posted along with the video recording from this as well. Yeah, so you don't actually have to take any of the notes if you don't want to. Okay, so let's get back to the problem we actually tried to like emphasize that we care about last class, which is the supervised learning problem, right? And this was roughly stated as we want to learn from randomly sampled batches of labeled data, okay? And all of these like 3 underlined terms, we're really going to try to formally like define in this class, well, 2 of the 3. Okay, and this is the diagram we kind of saw last time with a specific example, and this was the example of predicting house prices. Okay, so I had these like kind of more common people terms called experience, and the experience looked like this data of number of rooms and house prices, and this would be like your batch of data, and you would call this like the label for each one of these data points. Okay, and our goal was to produce this sort of knowledge, which I said was one sort of knowledge would be like this function that can predict new house prices. So this means you take in some unseen house, and specifically the number of rooms of some unseen house, and then you can predict its price. Okay, so what we're going to do today is we're going to formalize exactly what this looks like mathematically and like what these objects are, like what is this table of things and everything and so on. Okay, so this our step today is to do this arrow thing. And this is what it's going to kind of look like, this diagram. So we're going to call experience this word that's commonly used in machine learning called a data set now. So this is going to be our new word for experience. And it's kind of a slightly informal word, and the more formal object that we'll see it actually is this what I've put in purple here. So these are like the formal mathematical objects that we're going to be using to represent each of these different parts. Okay, so a data set is actually going to be this ordered set of ordered sets. Okay, and roughly speaking, well, I'll show you in a second. Okay, so that's what that mathematical object is going to be. Then there's this learner thing, right? So this learning, I'm going to call this program, or before I called it a program, now we're going to use kind of the word function and program interchangeably. And on the side here, I've highlighted is like the thing to kind of note is that the way to think about this is that programs, or I'm going to also use this word algorithms interchangeably, are things that implement functions. Okay, so in some sense, you have like some function, which is like, I don't know, let's say your function takes in a list and then it outputs, let's say, ordered list. You can write this function, it does this thing. But if you actually want to implement it, that's what a program would do, which is like the set of instructions to go from this input to that output. So for the most part, we're going to just kind of use these analogously until we actually need to define the set of instructions that perform this function. Okay. So for today, this learner thing is just going to be a function. And what is this function going to do, right? It takes as input this data set on the left, and it's going to produce this knowledge, which we're now going to call these three synonymous words, which are predictor, right? Why is it a predictor? It's something that like predicts, given input, it predicts something. Or commonly used in machine learning is a machine learning model. It's like the same thing, like ChatGPT is a machine learning model. It's also a predictor. Or sometimes the word hypothesis is used. So I'm just trying to get you all familiar maybe with the common words you're going to hear everywhere, and then so on. Okay, and that thing is also going to be represented as a function. Okay, so what I'm going to do next is I'm going to use some notation that I haven't formally introduced, but I suppose many of you will be familiar with, to actually define these things. That's what I'll spend motivating. And then after that, we'll go into the math of defining all the symbols and stuff. Okay, so here's the story I want to build. So we're going to start with looking at this data part here, this data thing here. Okay, so we want to make this a little bit more general and a bit more nicer with math. So what we're going to do is we're going to, first of all, we're not going to have like specific instances of things. We're going to just use variables to describe this data here. And what that'll look like is something like, I'm going to have an x1, an x2, an x3, and an x4. Okay? And then here I'm going to have a y1, a y2, a y3, and a y4. So all I did is just given these things variable names. So you can talk about it in a more general way. It's just some numbers or something like that. Okay, so now like in general, we're going to give this thing another name as well, which is going to be called the labels, right? As I said before. So these are the labels, and this is why it's called labeled data. And this thing here is now like this number of rooms. One way to think about it, it's like information about the object, right? And another word that people commonly use in machine learning is called the features. Or for here, first of all, it's just a single feature, right? So that would be like the number of rooms. Okay. So after that, in general, we're not only going to have like 4 data points, so we're going to also use a variable describing how many data points we have. And so the way I'm going to write this is there's going to be n data points, and this dot, dot, dot just means there's like data in between there. And similarly here, this dot, dot, dot means there's obviously like y1, y2, y3, up to yn. Okay, so we have n data points, and this whole thing is our data set, right? Okay, so the next thing is also this, I said there's like this number of rooms, but you can imagine you might have other information as well about this, like this house. So you might also have, for instance, its age or something like that. And you can have many other things like the size of it and stuff like this. So in general, these features are not just going to be like a one single number like this. So it's going to have another thing like this. And maybe I'll use like a subscript up here to describe that. So now I'm going to change this thing to be called features. And this is an example of when you have like 2 features. You can have more than 2 features, of course. Okay. And oftentimes we're going to, so the first thing to notice already is that notice how here there's some notion of like order matters already, right? So just to like maybe foreshadow what these things are, these things are going to be, when you use these curly brackets, they're going to be called ordered sets. And here there's some notion of order, because like the first item is really going to represent the first piece of information, like the number of rooms. And then the second item is going to represent like the age of the house. And let's say the third item represents something. So like this order actually means something here. And this is going to be like pretty important to note. Okay, and in general, we're going to just use some more general variable like x1 here to represent this object. This is going to be x2 and xn. And this is going to be representing this like tuple here. Okay, and so I'm going to use this word. You'll see it's come like in math. It's also used interchangeably, which is ordered set and tuple are going to be used interchangeably. Okay, so let's just keep going with notation. Yeah, so we have this like data set so far. We'll leave it at that for now, and we're going to go to talking about this predictor function next. Okay, and one thing before I go into the predictor, it's important to also point out like where these things come from. So here I'm going to say that each one of these x1s, or sorry, these xi's, so I'll be like x1 or x2 or anything, they're going to belong, and this is an element of symbol, they're going to belong to this set, which is this calligraphic x, right? And so I'll give an example in a second, and we're going to say this yi's, they belong to the set called the calligraphic y, and these i's are just elements of 1 up to little n. Okay, and let me just, cool. So all this means is that each one of these are in some sets. So some examples of this might be, so this calligraphic x might be, for instance, if you have 2 dimensions here, right? So like you have 2 indices in your features, it would be something like maybe r to the 2. And if you're not familiar with this notation, we'll go over it, but it just means it's a 2-dimensional real number. So it's just a number with 2 indices, so something that looks just like this, right? And then the y might be something like just a real number. Okay. And so this should fairly accurately like maybe represent the house example. Cool. Okay, so now let's move on to the predictor and come back to this in a moment. So I said this predictor is like this function f that has input number of rooms and outputs the price and stuff. But more formally, we're going to write functions with a notation like this. So I'm going to write a function f. And this function f is going to be, we're going to call it a map or whatever. And it's such that it takes values from x and it's going to map them to y. Okay, so like, this should make sense, right? Here you're trying to predict house prices, which is in this set y, and its input is the features, which is in the set x. And so this is going to be common notation we're going to use throughout for functions. So that just describes, this is also called the domain of the function, and this is the codomain. Okay. Cool. So let me see if yeah, so like one example, for instance. So let me so in blue, I'll just write kind of like the intuition. So this thing is like, so f is, we'll call f a function from features to labels. So this set x, calligraphic x, is the features, and then calligraphic y is the labels. Okay, and maybe one example is something like f of x equals to (2x plus 1), let's say, just like a function. So this is like, maybe we saw this last class, it's just like a line, right? So in this case, yeah, so in this case, I've assumed that this calligraphic x is only the real numbers, not the 2-dimensional real. So it just takes one number. Okay, so this is exactly what we saw in last class, where the input was just like the number of rooms, and then the output was the price. And here the slope is 2. Maybe that's not the best slope, but yeah, okay. So then we're going to need one more thing, which is this learner thing here. Okay, so, and as I said, this learner is also going to be a function. So let's write what this thing is going to be like. So Okay, I said we're going to call these like functions, potentially algorithms, and so on. So the notation we're going to use for this function is going to be this A notation here. Okay. And so this is going to be probably the most complicated part of the whole class, which is defining what exactly is this thing, right? So like at a high level, what's going on? Like this learner is taking in this object, which is a data set, and it's outputting a function, right? So if we just remember how this function notation looks like, which I'll go into more detail later, but like it's taking, it has a domain, which has to be data sets, and it's going to output, it has a codomain, which is what is it going to output? It's going to output functions. So the way we're going to write this notation is something like this. So what does a data set look like? Okay, so I'm gonna put something, I'm just gonna put in words for now, and then we'll define this thing. So it's gonna be, this thing's gonna be like a set of data sets, let's say, right? Because the domain is like a set of the objects you wanna take as input, so this is gonna be a set of data sets, and it's going to output to what is a set of functions. Okay, and here I'm gonna use some notation, which I will also introduce later, which is, this is going to be a set, so that has functions, and these functions are maps from X to Y. Okay. So I'll go over this notation also later in the class, but this basically says this is a set, and this is called like set builder notation, and it says this set is such that it has elements which are functions that are maps of this type. And this is exactly what we want, right? We want this learner here to output what? We want it to output predictors, and predictors are exactly of this form. So that should make sense. Okay. So now we need like a mathematical object that can represent this data set thing. And so far we have it in like this table format, and I don't know exactly, like, it's kind of weird, like how would I write the mathematical symbol of the table and stuff? So the common notation that ends up being used is exactly going to be this ordered set of ordered sets. And I'm going to introduce that now. So what that'll look like is we're going to first of all give the data set a label, or like, sorry, a name, which is just like a variable name. We're going to call it D. And this will say like a calligraphic D. And an example of what it would look like is going to look like this. We're just going to take everything in the table and just basically put it in an ordered set. So we're going to put the first thing, which is what does that look like? That looks like x1, right, comma, y1. We're going to put the second thing in there, which is x2, comma, y2, and up to the last thing. Okay, so this is basically how we're going to describe the data set throughout the whole course. It's going to be this, once again, and I'm going to go over this more later, but these these regular brackets, they represent that the set is ordered. And inside here, we have what we'll call like, often it's called like feature label pairs, right? And this is exactly the labeled part of the data, which is also ordered. Okay, so this is this data set object. So now I'm going to define exactly what does a set of data sets look like, right? So I need to explain like what does this D belong to, like what kind of set does it belong to? And what it's going to belong to is something that will probably be a little cryptic at the beginning, but we will define it. Also, is the size okay? It's not too small for anyone? Okay, so this thing, okay, sorry. So it's going to belong to some set, and that set is going to be this sort of complicated looking thing. So first of all, what does this thing look like? It has elements of this type, right? So the way to write elements of this type is going to be to write that the first element is in X, the second element is in Y, and to combine them, we're going to do this like mathematical process called the Cartesian product. So this produces like a single feature label pair, and then we have n of them. And so the way you would write this is now you could technically do like n of these Cartesian products, like all the way up and keep repeating it, but the common notation to write this kind of thing is going to be to the power of n here. And already notice how this is, okay, so let's just interpret what this means. This means you have this feature, this label, this is one pair, and how many pairs of them? You have n pairs. Okay, and notice how this is already kind of similar to what you've seen with real numbers, and you've probably seen this before, which is this kind of notation here, which just means there's two real numbers, for roughly speaking here. Okay. So that's what these things are going to look like. And now we can finally actually like plug in what this thing here is. So we're going to erase this set of data sets down here. We're going to write that it's this object, which is this feature label pairs. And there's n of them. And they map to functions which we're going to call predictors. OK. And then I'll just give it kind of like the English interpretation, which is that this A is a function from data sets to predictors. So this is how you should think of it. So I really hope to like kind of inject these like intuitive English understandings of all these math terms throughout, so that like it's readable and it makes sense. So yeah, so this thing really is taking this data set and just mapping it to functions. And this notation is going to be important all throughout the course. Okay, and maybe I'll just give one more example of what does it look like to take a data set and like use it to produce a predictor. Okay. So let's think of like what is maybe some like not so great predictor that you could produce using your data. So one way to produce a predictor is just like you have a bunch of these labels of like, let's say the example I gave before, which is number of rooms and the price that the house sold for, right? So one way to produce your predictor is take that, and then if you see a new house, then look at your previous data and see if you had a house with the same number of rooms. If you did, then just predict the price you saw. And if not, just, I don't know, predict that it's $0 or some random, whatever choice you have. So this would be like basically the learning process, which is called memorizing, right? You just memorize all your data, and then you output a function, which is your predictor, which just outputs basically what you've memorized. So if you see a new data point, and if it matches something you've seen, you're going to output that label. So we're going to write that a little bit more formally. So what that would mean is this thing, which is our learner, is going to take in as input the data set, and it's going to output some function f. Okay, and all that's left now is to define this function. And clearly this function depends on the data set through like the English words I've used. And so we'll just define the function, roughly speaking, to be like this. So first of all, it's a function of x, right? X is like the feature of a new house. And I need to predict what is that the price of the new house going to be. So what I'm going to do is I'm going to predict it to be yi, and this is if x equals to, okay, let me write this, if there exists an xi equal to this x that I'm just seeing. And then this xi, what is this xi? Where this xi yi is going to be an element of the data set. Okay, so let's just enter, and then otherwise let's like predict some price. I don't know what to predict. Let's just predict 0. Okay, so this is our function. Our function basically, what it's saying is I'm going to predict the price of a house I've already seen if its feature, like from maybe one interpretation, is the number of rooms matches the previous number of rooms I've seen. Okay, and that just means I've seen this number of rooms in my data set before. Okay, so I'm going to just, I guess, so that roughly outlines all of the, okay, let me just make this a little nicer looking. Okay, fine. I'll fix that later. Okay, anyways, the point is there's these 3 objects, right? Which is the data set, this predictor function you're producing, and the learner, which is taking the data set as input and producing the predictor. Okay, so there's obviously some things in here that maybe you're not familiar with, maybe you are. If you're already familiar, then this is like basically all I want to communicate in this class is like, this is how we're setting up the problem. And in particular, this is how we're setting up the batch part. So this is like the batch of labeled data. And this becomes really important that like we have proper notation for these objects. Okay. So this is going to be really the point of the class. All the math is just going to be to understand this notation. Yeah, and at this point, I don't expect everyone to know all this notation, but I want to ask if there's any like, let's say like overarching high-level questions about what's just happened. Yeah.
Ordered sets part, like I don't understand. Are you multiplying x and y and then raising it to the power of n? That notation?
Yes. So this notation is probably going to be the confusing thing that maybe not all of you have seen yet, and we're going to decode it in the rest of the lecture. So that shouldn't. And yeah, the question was basically like, what does this notation more or less mean? And this ordered set of ordered sets. And what we're going to do is we're going to formally define this operation on two sets called a Cartesian product. And once you see that, you'll see that then this power thing is really a shorthand for just saying I do the Cartesian product n times. So maybe just to like make this, maybe I can make this a little more clear, is that this R2 is actually equivalent to saying R Cartesian product with R. And this Cartesian product thing actually produces ordered sets. And we'll go over these details later. And the question you asked actually brings a valuable point, which is like, what is the point of defining these things as these ordered things? And there's like two answers. There's two things that are ordered here, right? So I think I've sort of highlighted why it's important to have order for the features and the labels. Like you have to understand that like this first index is the feature, and then the second index is actually my label for that feature. If these are randomly flipped, then you have no notion of what's the label of what. So there should be some order for these feature label pairs. And then secondly, it's not actually that important that this data set thing is ordered, but what is important is that you can contain duplicates. Okay, so in regular sets, we're going to see that you can't have duplicates, but here it's going to be important to see that you have duplicates. You can imagine if you like end up trying to learn about some like to predict some house price, and you see that the same house price, the same like house and the same house price keeps recurring over and over again, that's the valuable data to know, as opposed to just seeing it once in your data. Yeah.
Can you explain why the features are two-dimensional data, like one
Yeah, so maybe I can give an example of like, I'll just say it in words. It's like one example of features here. So we talked about number of rooms. If we just had one, that would be called you have one-dimensional features. And that would mean that x1 is literally just this thing here. But then if you remember like the wine classifying problem, there you had two pieces of information, which is like these two chemicals. And so now we want to have some object that can hold both these pieces of information. So there would be a two-dimensional thing.
So dimension can be like the number of dimensions is the features. Like we have two here, and it'd be like n.
Yes. So the question is, can the features be like of any dimension? And the answer is yes. So we're going to actually later on use some variable for that too, and that's going to be m. And that's just going to say that this is how many pieces of kind of like feature information you have. Like at a high level, like the intuition is that the more information I have in my features, the better I'm going to be able to do. But then what I'm going to suffer in is like the computational costs and stuff like this to do all this learning from this. But the more information is always better, as long as it's like proper information. Yeah.
The function f of x only works if there are precedents, like there's number of rooms, and if the function already has those number of rooms that it's going to work.
Can you repeat that? Sorry.
So the function f of x, you said that if there's a new number of rooms included into the function, it checks if there's something like that already in the function, then it'll be equal.
Yeah, so maybe I'm just like, was the question, can it work with previously seen numbers of rooms or something like this?
Does it only work with previously seen numbers?
Oh, no. So, okay, so this function, so the question is kind of like, does this predictor f of x, let's say in this example here, does it only work for previously seen numbers of rooms? So the answer is no. So that, like, this can take in any x, so I can write things even more formally, which is that where f here is actually a predictor. It's a map from x to y. So it's actually like the function you want. And this means that it should be able to work on any input in x, right? So that means x can be any number here. And then the question is, what does it do if it's not something that it's seen before? Well, what it does is it goes into this otherwise condition, and it just outputs 0. And so yeah, it's kind of a silly thing. It's like if I haven't seen that house, like that number of rooms, then I'm just going to output that the price is 0. So it does work on other x's. Yeah. Yes. So this is not what we're going to want, but this is like a classic naive example of like maybe some sort of learning. You just memorize what you've seen. But then it has this notion of like in machine learning where it doesn't generalize to new data. So that means like on new data, it just is completely useless. And we're going to have something to talk about like the quality of these things. And we're not going to do that in this lecture. So I guess I'm going to kind of jump ahead just for one note, which is that what we're going to miss in this lecture is to define what does it mean to do good learning. So I've defined what a learner is, but I haven't defined what it means for the learner to have done its job well. And we're going to get to that in a few classes, actually. So for now, we're just like have these intuitive understandings of what's good learning, maybe what's not. We're going to formally define that later. Yeah, and that's a very important thing I should probably have mentioned maybe earlier is that yes, right now we're just defining the process of like learning and what the predictor is, but we're not going to emphasize what the objective actually is, like in a formal way. Yeah. That's right.
Why does it matter that the rows in the database are in that particular?
Yeah, so this is a great question. So the question is, why does the data set have to have its tuples inside ordered? So like, why do these feature label pairs have to be ordered? Does it matter if really I saw like this house and this price as the first thing or the second thing? And the answer is it doesn't actually matter most of the time. I'm kind of overkilling this thing, which is I'm using ordered sets, but this is commonly what's used, is that I'm using ordered sets because of the fact that it allows us to have duplicates. So the formal word, and we're not even going to talk about it, is there's these things in set theory called multisets, and they're sets that allow for duplicates to be in there. But I didn't want to introduce these new terms and stuff like this. So for that part, we only care about the fact that it allows duplicates. And this gives us kind of like information like, oh, this house with this prices occurs way more often, so maybe I should like care about predicting that well or something like this. Yeah. But for the actual like feature label pairs, the order clearly does matter. Like you do care that this is, your feature is the first thing, the label is the second thing. Otherwise you'd have no idea what you're doing. Yeah, there's another question.
So is n the number of, or is it the number of data?
So n is the number of data points, right? So here, this is a feature, and there's n features, right, up to here. And then maybe the one thing that I've kind of hid here is that these features themselves are tuples. And I didn't want to write this inside the thing, because like if you just expand out what one of these guys is, you would see that one of these in the two-dimensional case, but maybe I'll write it for the most general case, it's going to look something like this. Oh, sorry. Where this is now some new. So yeah, so it gets like, you can see this math notation can get a little confusing, but this would be like the most formal way to write it. Yeah.
In the real world, there's cases where like even though a house is like different prices, so in this case we're just assuming that it's just based on the number of the house.
Yeah, so this highlights also a great point about the thing, which is that sometimes like okay, so in this example, you'd probably see with the number of rooms and prices, you probably see the same number of rooms in your data with totally different prices all the time. And that was an important thing to highlight that I kind of missed here, which is that in this naive predictor, I should have said like where this is the first index where you saw that thing. Because here you'd be like, okay, maybe I have multiple houses with the same like information, like number of rooms, but many different prices. So like, what do you pick? And then like more sophisticated learning algorithms might output like an average over this and stuff like this. And another way to like maybe like the intuition is that to reduce this randomness in the y, like the, okay, what do I mean by randomness in the y? What I mean is that if you look at the same number of rooms, let's say 2 rooms, you might see many different houses with different prices that have 2 rooms. So one way to like improve your understanding of why this variable in price happens is to introduce more information to your features. So maybe if you also knew like the size of the house and the location of the house and the age of the house and stuff, then the price would be much more accurate. You wouldn't have this large variability. And we'll see this throughout as well. Yeah. Yeah, go ahead.
Are we dealing with any sort of collateral?
Sorry?
Are we dealing with any sort of collateral domain?
Any domain?
Yeah, we're talking about rules, so is there like
Yeah, so here I've just naively written that, like, let's say this would be like, so X. So okay, the question is there like some cap to the number of rooms and things like this? And I've just naively written that you can have any number of rooms from negative infinity to positive infinity. This is like technically a little bit informal, but it's going to be how we treat things. Like, more correctly, I should write that it's like a natural number. So like it's a number of 0, 1, 2, 3 up to this. Yeah. So yeah, this is technically slightly incorrect, but we'll see some more details about that later. Any other questions? So yeah, it's good that there's all these questions. It's also not too surprising since I've just like wanted to high level motivate the thing. So there's all these like technical confusions. Yeah. Go ahead.
It's supposed to learn, right? The predictor is supposed to tell you like the prediction of the housing price, for example.
Yes.
So why is the learner function outputting 0 or something that it already has in the data set if it's just supposed to take in information? Like, what's the difference of the predictor and the learner if the learner function is already giving you a prediction?
So I'm maybe a little bit confused by the question, but it was something to do with like the difference between the learner and the predictor. And so maybe let me explain them one more time and then see if that clears up things, right? So what is a predictor? So a predictor is something that takes in just a feature, right? Like an unseen feature, and produces a label. That's all it has to do. Now did I say the predictor takes in a feature and produces a label? Now what is a learner? A learner is something that's going to output a predictor, right? And how is it going to output the predictor? It's going to use this data, or not, but like it can use the data, and it's going to output some function that depends on the data. So here, what happened? This thing is the learner. It's taken a data set and it's outputted a function. That's right. So F here is the predictor, and this is just the definition of what F is. What that means is like I've just defined what is its behavior on every input value X. And notice how this thing, maybe I could be more explicit, and I could write that this thing depends on the data set here. And this is like commonly used, you put in the subscript. And why does it depend on it? Because it's using the data set as knowledge onto how it's going to predict things. And once again, we're going to use much more like, I don't know, more like better predictors in some sense than this, which is it's not just going to naively memorize all the data. Like one example that we saw in the previous class was this notion of a line, like a linear fit. So one example would be output something like this, like a line, but use the data to choose, let's say, the slope. So we're going to be talking about that in this class. Like, how do you choose the right slope to fit the data? Yeah, go ahead. Right, so the data set is equal to an object like this, right? That is correct here. This object is a set, okay? So we're going to define Cartesian products later, but like this object is a set, and it is a set of all possible data sets, which means all possible ordered sets of ordered sets. So it actually contain, so like what this object would look like maybe is like, okay, so it's going to be like a set, and in this set, it's going to have like all possible data sets, and this is a little bit crude to write it, but like there's data set 1, and there's data set 2, and then all the way on to like all the infinitely many possible data sets. And then this example is, right, that D is just one element of this giant set of things that are data sets. And these things that are data sets are these complicated looking objects like this. Okay. And so maybe to step back, like the reason this is like, I really want to emphasize this, and it wasn't quite as emphasized the like years before, and maybe I'm doing a disservice, maybe I'm not, but like it's going to be crucial because what's going to happen later is we're going to have to pick a learner, right? We're going to have to choose like what is a good learner? Like should we pick this learner? Like maybe not, but like how are we going to evaluate? And it's like one important thing is going to be like if the data set were to change, right? Because I don't know what data I'm getting. Like if the data set were to change, because like I'm just randomly given it, does my learner still do okay? And this is going to be really an important question that comes up, which means that like if this D were to change, does my learner still, like, how does it behave? Like, what does it just catastrophically fail or something like this? So it's going to be very important to actually understand what this object is and the fact that it can change and things like this. So that, like, once again, I really emphasize to like make sure you understand this like kind of intuitively and the notation at the very beginning of the course, because like everything else will just build on this and it'll be, yeah, it'll be, I'll try to explain the intuitions about like what's happening, but maybe without the math, it'll be a little bit more challenging. Okay. Cool. So that was a good amount of questions. Hopefully that cleared up some things. Let's see, there might be some questions online. So someone asked the question as well, which was a while ago. Yeah, so the question was something like, just to make sure there can be multiple features, but only one label. And the answer is like, yes, basically you can, so this thing, which is called the set of, this would be like the order set of features, it can have multiple features. So like number of rooms, and for instance, the age of the house, and then you will have just one label for that multiple features. Okay. Cool. And then there's, okay, before we move on, there's just one last thing I want to mention, which is going to be kind of, oh, you can ask your question, sure. So, yeah, I mean, it's technically possible. Like you could imagine, I don't know, X1 itself being some complicated object, which is like a photo of the house, let's say, and maybe you represent the photo as this giant, hopefully it doesn't confuse everyone, but you can imagine, like, these things are like kind of arbitrary objects. And I was just about to actually talk about this detail. So they can be like anything. Like I said, they're just these nice simple things, which is like a number, the number of rooms, or like, for instance, the age of thing. But they could be anything. It'd be like, let's say a picture of a house. So how would I represent the picture of that? Like I could, maybe I would represent, yeah, I could even put that as like one detail, and that would be like this giant thing, and maybe every pixel value in there, and yeah, and I don't know. So yeah, but that's going to turn out to be a very unpleasant way to model things. And maybe just to build up on that is, we're actually going to make this extra assumption, kind of, which is that we're going to give these ordered sets, these features, some extra structure, and we're going to call them vectors. Okay, and all that a vector is, and I'm going to go over this, is just an ordered set with the ability to add things, like add these order sets together and multiply them by a scalar, right? So we're going to, in this class, basically always talk about like these real numbers. And you've probably already seen this in your previous classes. This thing is a vector space, and elements of it are going to be called vectors. So for instance, this thing is going to be called like a vector from R2. And what, like, the only reason, like, all this notation means is that I can add two vectors together. So I could add two features together, or I could just multiply them by some amount. And this is going to turn out to be very, very useful for when we try to choose what is a good predictor. And the reason why is because if you have these vectors, then you can do like linear algebra operations, which means you can like multiply them by matrices and whatnot, and then you can optimize and find good things. So like it just makes things mathematically very clean. So with that being said, what I'm going to add is that each one of these xi's and stuff, I'm going to use this kind of arrow at the top symbol to denote that these things are vectors. So now they're not just ordered sets, they're going to actually be vectors. And so I'm going to add this. So this was the last detail I wanted to add. Yeah. Okay, and that's like not a super obvious thing why you'd want to do, but like you'll see in the future that it's very nice if you have these things called vectors, because we're going to be able to like do operations on them. Otherwise, you just had ordered sets, and if like the ordered set was like cat, comma, dog, comma, eagle, imagine like what does it mean to add a dog to a cat or something like this? It doesn't make much sense. Okay, so this definitely took longer than I expected for this part, but that's good to know. Cool. So the goal of the rest of the class, which we will definitely not finish today, is to define these objects. Okay. And in particular, like to define to define what, let's say, like this object is, like what is this, like what is this function notation, and like how to interpret this formally. Okay, so let's get into that. Okay, so it all begins with sets. Okay, and maybe I'll give like a very brief story, which some of you might be interested in, some of you might not. So there's this, so like when we define sets, it's actually this whole branch of math called set theory. And we're not going to go into any of like the proper details of any of this, but I did want to mention that like this is actually kind of a very like abstract and foundational part of maths. It's really beautiful, and here are some like interesting facts about it. So like all of mathematics is actually built on these things called axioms. So there's like these underlying axioms of math. And these axioms actually say that every object in math is represented as a set. And then there's a couple of different operations you can do with these sets. And from there on in, you build everything. So like all the numbers are represented as sets, all the functions are represented as sets, and so on. Totally unnecessary, but just like all I wanted to point out is just like, it's kind of like at the heart of everything. There's these axioms, then everything assumes that everything's a set, and that's how all of math is built on. So it's like, that's kind of an interesting note. Yeah, and maybe the other interesting thing to note for those people interested. So like the interesting thing about this like specific axiom system, which is called, so the one that all of math is built on, and once again, this is totally unneeded for this class, is called this axiom system called ZFC set theory. Okay, and the interesting thing is that we actually don't know. Okay, so there's this amazing result that someone called Gödel showed back in like 1930, and it's called Gödel's incompleteness theorem. And what he basically showed is that, okay, like we have this system of math and stuff, and right now we don't know if there's statements for which there can be a contradiction. So what this means is we don't know if our whole mathematical system is a consistent system or not. Okay, so what's a consistent system? What a consistent system is one where any mathematical statement, so say something like 2 + 2 = 4, I can either say that that's a true statement or a false statement. So that's a consistent system. An inconsistent system would be one where like 2 + 2 = 4 can be true and false. Okay, and so right now, and like actually, so what Gödel showed is that so right now the ZFC set theory, we don't know if it's a consistent system or not, which means that there might be some statements for which they can be both true and false, which would be a very big problem. And what Gödel's incompleteness theorem showed is that if you were like, there's no way to show whether this is true. So there's no way for us to actually find out whether our math is consistent or not. But if we were to find this like inconsistency or this contradiction, then obviously we would know this. So basically, like all that being said is that everything's based on the set theory of axioms, and for all we know, it might be an inconsistent system where there's like statements in there that are both true and false at the same time, and everything would break down. And yeah. So anyways, that's like the little side note to set theory world. But we're not going to work with any of that. But that's a fun fact. Okay. So the way I'm going to go through this stuff is now I'm just going to kind of give you definition, like the names of things. And then I'm just going to show a bunch of like examples of them. We're not going to go over like formal math statements of what these objects are and define all their properties. We're just going to give you some examples, and hopefully that will be like sufficient to understand what these things are. Okay, so the first object is going to be a set. Okay, no other questions? Cool. So the first object is going to be a set, and all that a set is just going to be a collection of, and this is the important part, of distinct and unordered objects. Cool. So some examples of sets. And the one we're going to use throughout is, for instance, we use these curly brackets to denote sets. And an example of a set is the set of numbers 0, 1, and 2. Okay. So since I said these things are distinct, it turns out that if I have the same element in the set, these are the same sets. What that means is if I had the set 0, 1, 2, and 2, these are the same sets. Okay. And similarly, I don't need to just have numbers. These are collections of like objects. So I could have things like cat, comma, dog in there. whatever object you want, you can put in there. And since order doesn't matter, I can just change the order of these things, and they're still the same set. Okay, so this is clearly in contrast to what we saw already about these ordered sets. And the reason I'm starting with the set stuff is to like get to the ordered sets, you kind of need to know what a set is first. Okay, so this is common properties. So what are some sets you know of? So one set you might know of before, and we're going to use this notation, is this bold kind of n. And this is the, maybe I'll define it, it's the set of all natural numbers. Okay, the set of all natural numbers is basically these positive integers. So 0, 1, 2, and it's actually like formal notation to write something like this. So it keeps going on till the largest possible number. Okay, and this thing is called the natural numbers. And we'll use this notation quite frequently throughout the course, this n, bold n thing. There's another set called the real numbers. Okay, and I'm not going to define it formally in this class. It's actually a whole, like if you take a real analysis course in math, it's going to be, it takes like a good amount of lectures just to define these things, and they're defined based on sets, which are, the natural numbers are defined as sets, and then the real numbers are defined as natural numbers, and it's actually a whole complicated thing. But the way to think about it is just it's every single number you've ever seen, and yeah, it's any number you can think of. And we'll talk about examples in one quick second. So these are the real numbers. And yeah, I'm going to define one more type of set, which we're occasionally going to use, which is this thing called the empty set. And so this thing just has nothing in it. Okay. So I'm defining all these like really foundational things, and you might at this point still be wondering why in the world you need to know all of this. And hopefully like you'll see that soon enough we'll build to the things we saw in the class, and then knowing this foundational thing will actually be very useful to kind of interpret everything, because otherwise it's very hard to decode what's going on later. Okay, and this might seem very simple for now. So we, just like in regular calculus and stuff, we use variables for numbers. We can also use variables for sets. And all that means is instead of writing like an actual set, we can just say like this variable is a set. And the common variables we're going to use is this omega. And then any of these calligraphic symbols. So you've already seen me use the calligraphic x, this calligraphic y, maybe a calligraphic z. These will probably be the main ones I use. Okay. So once again, a thing on notation, this is going to be important to just like, it's important throughout all math, is like, there is actually some like, I guess, what's like common practices to what you call different different variables and things like this. And so these calligraphic things are going to be sets. These lowercase symbols like x, y, and z are going to be numbers usually, or maybe like vectors if you put the thing at the top. And then we're going to see that these capital letters later on will be used for random variables. But we won't do that today. And so these are like important things to remember. Okay, cool. So examples. So, I mean, like this thing can be anything. One thing it can be is I can give it a value, which would mean like give it a set, and I could, for instance, give this x could be this set that we talked about above. Now I can just say like things about this calligraphic x instead of saying things about 0, 1, and 2 and writing this over and over again. Similarly, if you had a variable x, you could say like my x is a real number, and then I could just talk about x throughout as like this object. And throughout this thing as well, I'm going to maybe use this omega to denote this cat and dog. Cool. Now, there's another operation called cardinality. And all the cardinality is just the size of the set. So this is like size of the set. And the way we denote this thing is with these like two bars, and I'll show some examples. So you might ask, like, what is the size of this calligraphic x? Well, the way you would write this is the cardinality of x using these two bars on the side is 3. Just the number of elements in there. Okay, so here's some, we're gonna get some already an interesting new, like other math result in some sense, which is the size of this thing is 2, right? Okay, that's still like as expected probably. Here's another set, the empty set. The size of the empty set, as expected, it's empty at 0. Okay. Here's another set, the natural numbers, right? We've seen the natural numbers. And I said this thing's like all the numbers from 0 to like the largest number. So this set, there's actually like this formal symbol in math called infinity. Okay? So this is one, so the size of natural numbers is infinity, okay? And now I'm going to kind of loosely use the same symbol to say that the real numbers are also infinite. Okay. It turns out that this was actually a little bit sloppy, and here's just like a useless thing for the course, but like, I guess another fun fact about math, which is the following, that this cardinality is not equal to this cardinality. Okay. So some of you may have seen this before, and I just want to mention maybe another like fun fact about this. So the size of the natural numbers is called this like countably infinite. The size of these real numbers is called uncountably infinite. Okay. And another fun fact about math is that you might think that every single like question you ask in math you can prove. So something like, how many primes are there? Or like, I don't know, like how fast does this algorithm run? Or something like that. You can prove every single math statement, you might think. But it turns out that there's this other fun quirk about math, which is that there's some statements in math which there exists no proof. It means that you literally cannot write a proof in math. And it turns out that this question exactly, which is the question of, is the natural numbers, like how many infinities are there between the natural numbers and the real numbers? This is a foundational question called the continuum hypothesis in math. And it turns out that this question, someone actually, what they did is they proved that there can never be a proof answering this question. And there's many other questions in math afterwards that were also like shown that you can just never have an answer. So, you know, like one funny way to cop out of like proving something is you can just say like, oh, maybe this thing is just never provable. So like if you ever can't prove something, maybe it's just the case that it's another one of these questions that are just never provable with math and you can't solve it. So it's not your fault. Okay. Cool. Okay, now we move on to things called elements or subsets of sets. Okay, cool. So these are the symbols we're going to use for it. They look like this. This means element of. So now we're seeing things that we've already seen before that I was using at the very beginning of the class. I was saying like things are elements of a set. So this means element of. This means not an element of. This means subset of. And this means not a subset of. Okay. Examples. Once again, all of this should seem very simple, which is that cat is an element of omega. And here I'm using this variable notation. Notice that omega is this thing, so cat is clearly in that set. Okay. However, note that, okay, and maybe one thing is like, the way this reads is cat is an element of omega. Okay. Notice that cat is not an element of calligraphic X. Why? If you look at calligraphic X, it has numbers, not cat in it. Okay. So simple enough, right? And so now we can actually sort of give you an idea of what the real numbers are. I can just like write things. So now I can say what's in the real numbers at least, instead of defining the set explicitly. And some things in the real numbers are like 0 is in the real numbers. 1 is in the real numbers. Some other things are like negative numbers are in the real numbers. Fractions are elements of the real numbers. Like also decimal point things are in the real numbers, and also irrational numbers such as pi is an element of the real numbers. Okay, and maybe one other thing to note is that infinity and negative infinity are not elements of the real numbers. Oh, not. Cool. So that's really all you're going to need to know about this. Real numbers, I'm sure you never thought about maybe at this level bigger, but like, yeah, these are things in the real numbers. Just think of it as any numbers. It'll be used throughout. Okay, this is the element of notation. Now there's this subset notation. So if you recall what calligraphic X was, so I'm just going to write what it was here one more time to remind you, which is that it was 0, 1, and 2. So this calligraphic x, you can now write it's a subset of, well, it's a subset of the natural numbers, right? And the natural numbers are all the numbers, like 0, 1, 2, 3. So this is inside that set. It's a smaller set, is the way to think about it. This calligraphic x is also a subset of the real numbers because the natural numbers is a subset of the real numbers. Okay. So like it's some way to kind of communicate that this is a set that has everything in the previous set and potentially more. And for example, x is definitely not a subset of omega, because if you recall what omega is, it has cat and dog and does not have the numbers 0, 1, and 2. So it's not a subset of it. And like here, the usual understanding of this is to draw a picture. And so the picture would be something like this, which is like maybe I'll draw the natural numbers as this set. So a lot of times sets are just going to be communicated as these like circles. And then the thing that's larger than the set of natural numbers is the real numbers. Something inside the natural numbers is this calligraphic x, which is 0, 1, and 2. And something outside all of this stuff was omega, because it was just a cat and a dog. It had nothing to do with numbers. Okay. And then some other things just about the notation is that I'm also going to say like a subset means also subset or equal to, just throughout. So x is actually a subset of itself. And similarly, like omega is a subset of itself. So this will be correct to use. Sometimes people use this like equal to notation. We're just going to avoid that and just say this means that as well. So this is really subset or equal to. Okay. That's all we have about these simple things. Okay. Next, we're going to move on. So far we've seen these like sets of like, except for the real numbers, we've seen these sets of like discrete, like finitely many things or like discrete things. So you can also have like these continuous things, and the ones we're going to work with in this course are called intervals. And already, like for anyone that's taken anything in probability, I'm just going to kind of like foreshadow why this might be sort of important, is you might remember there's like these distributions over a random variable. Like there's a normal distribution, right? Which is like this bell curve thing. And then there's like these Bernoulli distributions, let's say, which is like flipping a coin. So you can see flipping a coin has like a discrete set of outcomes, which is like 0 or 1. But like the bell curve has this like continuous set of outcomes. So we're going to need to talk, and we're going to say like, what is the outcome space? Like what can the things happen? Just and so we're going to need intervals and these like continuous sets for continuous distributions, and we're going to need these discrete things for discrete distributions. So just like another reason of why all these objects are very important to define formally for later. Okay, and the way to think about this object is just going to be a continuous subset of R, like roughly speaking. Okay, and like, let's see some examples. So it turns out there's also like some naming, and here is where you're going to really get confused if you don't pay attention with math notation, unfortunately. So yeah, I'm going to point it out in 1 second. So here everything's fine so far. So these are called closed intervals. Okay, and a closed interval looks like this. It's a subset of the real numbers. And usually the way to understand this thing is you draw something like a real line. So this thing extends out to negative and positive infinity, but not including them, as we said before. And then if you have, let's say, 0 here and 1 here, what this interval would be including 0 up to 1 and including all the values in between the two things. Okay, so now here comes the fun. All right, let me note one more thing. So this interval, since it is continuous, it is not a subset of the natural numbers, right? Natural numbers would just have the numbers 0 and 1. This actually has every possible number between 0 and 1. Okay, so now here's where the notation gets really unfortunate. So not in set theory, but in this field of calculus and more formally it's called real analysis, is they use notation for intervals. There's these things called open intervals, and the notation they use there is also these regular brackets 0 and 1. Okay, and so here you're going to have to be very careful to notice what is the context of the problem. Because I haven't got to the definition of an ordered set yet, but as you remember from the beginning, an ordered set also used this notation. Okay, and they're both sets, and so it gets really, really confusing. But you're going to have to like basically understand from the context which one you're working with. And so here, this open interval is not the ordered set, 0 and 1. It is actually the interval of all numbers between 0 and 1, but not including 0 and not including 1. Okay? So for instance, 0 is not an element of this interval. And once again, the classic way to understand this is through a picture. And here you would have 0, you'll have 1. And now you would draw something like this, and little circles noting that you like don't include 0 and 1. Okay, and then finally there's going to be this thing that we also use, which is like when one side is open and one side is closed, which we're going to call half open or half closed. And this would be something like 0 to 1. Or another example is, and this is why this might be useful, is 0 to infinity, but not including infinity. So this would be like all of the positive real numbers. Okay. And once again, the picture is almost the same story. You can probably guess 0, 1, and then here you're including 0, but you're going to 1 and not including 1. Cool. So these are all the like sets and the basic operations that we're going to do with them. And now there's some more maybe complicated operations, not so complicated. Yeah, there's a question. Oh, excellent. Not subset. Thank you very much. I think I said in words, but I wrote the wrong thing, and that probably confused people. Yes, that is definitely not a subset. Oh, and similarly, this thing is a subset of the real numbers. And the important thing here is that 1 is not an element of the set. Cool. Okay, so next thing is there's operations you can do on more than one set. So like you can do things with multiple sets. And these operations are called unions, intersections, and complements. And once again, these will be like a little annoying to learn now, but like they're important operations you'll kind of need to know to like manipulate these sets. Like, okay, let's imagine, let's draw some things again. So you have these natural numbers, right? So now let's draw one set, which is like the set we've seen before already, which is the set of 0, 1, and 2. And that's inside the natural numbers, right? Now suppose you also want to draw like another set. And it like some of it's in there, like they some of them they share some elements, they don't share some. So maybe this set sharing some of them would be the set 2 and 3. So they share the number 2. They don't share the number 3. And you can already see there's going to be some operations you want to be able to do to talk about these things, and these are going to be exactly the ones I just talked about here. So the union, yeah, let's just do it with so the union of 0, 1, and 2 with, for instance, this set that we see here is going to be just take all their elements and put them into one set. So it's going to be 0, 1, 2, and 3. Notice how the duplicate 2 just gets removed because that's in sets there's no notion of duplicates, so there's no point of writing the second that thing there. Okay, so what does that look like? What that looks like is it looks like this set. Okay. Cool. Next thing is these intersections. So 0, 1, 2 intersect 2 and 3. What does that look like? It's the thing that they have in common, as the word intersection might indicate, and that's 2. So that set would be like this thing here. And that would just contain the number 2. Okay. And then what's left is the set. Okay. Oh, this is not the word I meant to put there. Sorry. This should be set subtraction. So you can subtract sets. And notice that's also a different operation than what we've seen here, and that would look like 0, 1, and 2. And the set subtraction symbol, okay, so maybe I'll write these symbols. So there's the union, there's the intersection, and then there's the set subtraction. And the set subtraction of 2, 3 gives us a new set now again, which is you take the set on the left, you subtract all the elements from the set on the right, and you get the following set, which is 0 and 1. And so finally, this set is also a different set, which is this guy, but not including 2. Okay. So that's that. Cool. So that's those things. And now there's going to be one more operation that you probably heard of, and this one's a little bit funny to define. It's called the complement. And this notation is just like a superscript little c. And at the bottom of the set. So it's a set to the c. And to define this thing, here's like an important note, which is that you need to have this notion of a universal set. Need to define a universal set. And so what does this mean? Just like, I'll just give it as one example. I think that will clarify everything, which is that if the space, it's like the universal set, just like the space I'm working in. So if this like, I'm just going to use this calligraphic U thing here, which is that if my universal set is equal to the natural numbers, just like I've seen in that picture over here, this is like my space I'm operating in, then the complement of some set, so that would be written something like, let's say, this calligraphic C, which just to remind you is the same thing as 0, 1, 2 complement. What is that? It's just everything in the natural numbers excluding this set. So this would be like one other way to write this is you would write this universal set and you would set subtract the calligraphic X. So what do you get after all this is you get something like the natural numbers but missing a few things, which is it starts at 3 now and it goes up to all the way up to infinite, like all the natural numbers after. And so what that would look like in this kind of drawing is it would look like basically like everything outside here. And also including this region. So that would be like the complement of this set 0, 1, 2, where 0, 1, 2 is this thing. So just like everything outside. Okay. Good. We're actually making decent time. Yeah. Yeah, so you're talking about this object, right? Yeah, so sometimes people will, okay, so first of all, the name should kind of describe it, which is called set subtraction. Sometimes people will also write this as just a minus sign. And you should just think of it almost like a minus sign with numbers. And then the interpretation is you take the set on the left, and from the set on the left, you subtract all of the elements that are in the set on the right. So this would mean you look here, you have 0, 1, and 2. You look here, you have 2 and 3. And so from this set, you subtract any elements that are in this set. So that would just be 2. So 2 gets subtracted from here, and then you are left with just 0 and 1. Yeah, so that's all of it. It's just like, if you have 2 sets, sometimes you want to remove a part of one set by saying remove the elements that are in the other set. So this kind of thing is also common. And once again, I want to just kind of hide from writing like the formal definition. Well, we'll be able to write it in actually 1 second once we define this new kind of operation called set builder notation. Okay, and so for better or for worse, this notation is really convenient, gets used in a lot of places, and you'll probably see the value of it in just a couple, maybe I guess in the next lecture on Tuesday. But we'll end on this thing, which is called set builder notation. And I use this at the very beginning of the lecture to define some sets. Okay, so this is what it kind of like roughly looks like in words, is you'll write a set, and then inside you'll write the element types. Then you can write as many of these things as you want, but basically what this like bar means here is that this means element types such that, and that's what the bar means, this bar thing. It means basically in words, it means such that. And then it's such that some property holds. And so such that some, what people write is a condition holds. And this makes writing some sets way easier. Okay. So what are some examples of things that have become much easier? So suppose I wanted to write, okay, so I want to write, so these are the element types. So they're like, let's say x that are elements of the natural numbers, right? And I want x that has some property. And so like, I would write the property here. And that property, let's say, is that x is less than or equal to 2. So right now, you're not going to see the true power of this thing, because what you're going to get out of this thing is you're going to get all the natural numbers, but only the ones that are less than 2. So what are those? Those are exactly the set we've been working with this whole time. So 0 and 1 and 2. That's one way to write that set. These are equivalent things. But now let's say you want to write something like, let's say you want to write all of the even numbers, right? Like maybe that you can still kind of write informally, but like the formal way to do this with the set builder thing is you'd say it's all the natural numbers such that when you take x and you divide it by 2, you get 0. And that would be, maybe you could still pull it off because you could recognize the pattern here, and it would be like this kind of set. Sorry? So the modulus. Oh, yes. It should be the mod. So, okay, let me just avoid this whole confusion. And it's also totally fine to write things like such that x is even. So this kind of thing is also totally fine, and it's much more interpretable. And so here you would have the set that I was saying. Okay, and to end, we have one more example, which is, here's a much harder one maybe to write, which is that x, element of the natural numbers, such that x is prime. And so this is the set, which would be very hard to write, which would be like all the prime numbers, so like 3, 5, 7, 11, and maybe somebody that knows prime numbers would like understand what this ... means here, but like otherwise this becomes kind of a cryptic way to write it otherwise. So if you were to, what I mean is if you were to just write this to indicate the prime numbers, that might be a little bit weird. So this is perhaps the first place we see the power of this. And just to like reiterate where this was maybe used is that right here, this is like the set builder thing. It's that these function things. Okay. Anyways, that's the end of today. Thank you.